Assalamualaikum and good day all. We are going to continue with the topic of atoms, elements, compounds and mixtures. In order for us to talk about atoms, elements, compounds and mixtures, we try to relate them to what we see around us every day. Everything around us is actually atoms, elements, compounds and mixtures. So in part 1, we have talked about the great works of all the people who brought us to the atom that we know now. Okay. Before we proceed, let me first clarify. The acceptable model of atom is the one with electrons moving within its cloud with various orbital shapes, which we will look at after this. But it is still widely common for us to see this kind of atom model because it is easier to draw, easier to understand, and easier to discuss. I will show you the simulation of the electron clouds later. Okay. So, as we have been discussing before, the atom that we know now is the smallest part of a substance that cannot be broken down chemically. So, atom is somehow can be separated using other techniques such as laser, but it cannot be broken down further chemically, at least for now. So if you look at the electron model, as you can see, it consists of nucleus, and then we have nucleus consists of proton, which is positive, and also neutron, that is neutral. Okay, and around it we have the negatively charged electrons. So all of these are the electrons, and it's moving around the nucleus in certain manner. So the nucleus, as I said before, the proton and the neutron is very, very dense. And heavy. Okay, the majority or most of the weight of the, you can say almost the whole weight of the atom comes from the nucleus. But this part where the electrons are moving are very loose and big. Okay, but mostly because of the electrons of the because of the movement of the electron, mostly it's just space. And now it is also believed that the neutrons and protons that is making up nucleus are made of quarks. Okay, quarks. What is quarks? Quarks is a group of subatomic particles believed to be among the fundamental constituents of matter. So up to today, quarks and electrons are the most fundamental known components of matter in the universe. There might be more, but at least till now, that's the most fundamental or the most basic things of atom or matter that we know. We can also imagine atom is very, 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 very small. We can imagine atom to be we can imagine the atom to be one out of a million carbon atoms wide if you look at your human hair. So basically, if you take out your hair, you look at the diameter of the hair, that is probably made up of million carbon atoms. It's not even the smallest atom, but carbon atoms. So atoms are very, 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 very small. Okay, So there are a few things that you need to know in an atom. Okay. First, atomic number is equals to the number of protons. So you'll see that we always refer to atomic number in describing an atom, especially in the periodic table. Okay? So if you look at the periodic table, okay, so the number in the periodic table, like 1 for hydrogen, 6 for carbon, so that actually represents only the number of protons. Next that you have to know is the mass number, or how heavy it is. Okay? So that is usually represented by this. Okay? So that's how heavy the atom is. But you have to also remember that mass of an atom, or how heavy the atom is, always rely on the nucleus. So that's why we refer to the number of protons and also neutrons. The reason is because, as I said before, nucleus is very dense and heavy. So the mass comes from the nucleus only, which is the number of protons plus the number of neutrons. And then you have to also know that all atoms with the same atomic number, they always remain the same. For example, hydrogen, okay, hydrogen always has 1 proton, and carbon always has 6 protons. But sometimes some of the atoms can also exist with different number of neutron. Okay, for an example, hydrogen, if it has only 1 proton, okay, you can see only 1 positive sign in the middle, so it exists as hydrogen. Sorry, 1 proton and 0 neutron. If hydrogen exists as 1 proton and 1 neutron, okay, you can see that 1 positive sign and 1 the black dot, so that represents neutron. So it is known as deuterium. If the hydrogen exists as 1 proton and 2 neutron, so you can see 1 plus and 2 black dots, it is known as the tritium. So this is known as isotopes. So hydrogen, deuterium and tritium are isotopes. So they are basically the same element. Okay, they are the same, but the only difference between them is that they have the different number of neutrons. Because they have different number of neutrons, okay, so let me use different color. So because they have different number of neutrons, okay, and as I said before, neutron is also heavy, therefore they have different mass. Okay, so the atomic mass is different for all the isotopes, even though they are fundamentally the same element. Okay, and this is the idea that the electrons also behave as wave. So it is imagined that the electrons move so fast that we see them as what we know as electron cloud. But as I said before, for an easy representation and for an easy discussion, we can imagine them in such a way that we can see the electrons moving around it. So the electrons moving around the nucleus on its own orbital. But in reality, it moves so fast that we cannot actually see this kind of behavior. Instead, what we see is that the electrons exist as what we know as electron cloud. Which brings us to the study of quantum mechanics. Okay, so quantum mechanics. Okay, quantum mechanics is a study that describes electron energies and locations by a wave equation. So the basis of quantum mechanics is the concept that we cannot specifically know where the electron is. Okay, but because we do not know where the electron is, what the best thing we can do is to predict where they are using Schrödinger equation. So basically, Schrödinger equation predict the most probable area of finding electron, where electron most likely to be. And in this equation, the probability of finding electrons around the nucleus is described by wave function, because we see the electrons movement as wave. And each orbital around the nucleus is represented as one wave function. So basically, you can imagine this. Let me use different color. So you can imagine that when we have nucleus in the middle, but then we have a lot of orbitals around the around the nucleus, and each of these orbitals is represented by one wave function. Okay, so if you imagine the electron cloud, as I said before, it is impossible to know specifically where the electron is at one time because they exist as a cloud. So we can only predict the most probable area or the probability to find the electrons. That's the best we can do. So till today, there are 4 kinds of orbitals known or accepted by the scientists, known as the S, P, D, and F orbitals. Okay, S orbital is the simplest, and it has the lowest energy. So remember, as I said before, lowest energy meaning that it is closest to the nucleus. So S orbital is inhibited by less number of electrons, and it is modeled to be spherical. P orbital is the second one, shaped as a dumbbell. So it looks like a dumbbell. And there are 3 kinds of P orbitals, and you can imagine them as being localizing on 3 axes X, Y, and Z. So we have 2px, 2py, and 2pz. And this is d orbital. So d orbital is like again like a dumbbell shape, elongated dumbbell shape, and it has like a circle or nucleus at the center. Okay, and there are 5 different kinds of d orbitals. we have dyz, dxy, dz squared, dxz, and dx squared y squared. So it is also depending on where the electron clouds are localized. And finally, we have f orbitals, and I'm not showing them here. I'm going to show them in the electron cloud simulation later. Okay, this one. So I just want to share this modeling. Then on the shapes, okay, so you can see that they are moving. If you look at the s orbital, okay, so we start from the bottom. So this is the lowest, the bottom one is the lowest s orbital. So it has only one circle. And as we go up, the number of orbitals or the number of circles just increases. But they still exist as circles, okay? And then we have p orbitals, okay? So they are, as I said before, dumbbell shaped. So, and then we have d orbitals, okay? And we also have the illustration of the f orbitals here. So f orbitals is the most complicated. Okay, so that's everything about electrons. Okay, so even though understanding exactly how the atom is impossible, but with the current technology, actually has made it possible to now visibly see the evidence of atoms, even though they are very, very, very small. But at least we can see the evidence that they exist as how we are trying to understand them till now. So I just want to show you guys this video to give you guys some idea of what we can actually, or how far have we proven the electrons that we know right now.
Have you ever seen an atom? Seeing as everything's made of them, you have. But have you ever seen one on its own? Over time, microscopes have become more and more powerful, allowing us to see deeper into the world of the ultra-small. Traditional light microscopes can be used to see things like these onion cells and the structures within them as they divide, pulling apart their chromosomes. But scientists have come up with a whole host of clever methods to observe far smaller things. Using beams of electrons instead of light, we can generate detailed images of chromosomes themselves. Recently, groups of scientists around the world are becoming able to see materials at the most fundamental scale, the atomic. One group from the University of California in Los Angeles have been getting up close and personal with nanoparticles of platinum, just a few nanometers across. Each of the tiny dots you can see here are actually individual platinum atoms. But researchers didn't stop at a two-dimensional picture. By imaging over 100 slices of the nanoparticle at different angles, then removing the noise with a special filter, they were able to map the location of almost every atom. The information was used to create a three-dimensional reconstruction of the whole particle in unprecedented detail. It may look blurry, but this particle is estimated to contain over 27,000 atoms, and so, like flies in a swarm, they appear to merge together. Every so often, though, we see the platinum's atomic structure align, granting us a moment of clarity. This technique is being used to analyze tiny irregularities in the structure of the particle called dislocations. Dislocations are subtle, like the misalignment of the green and red layers of atoms in this particle. But nonetheless, they can significantly change the properties of materials, with effects ranging from a change in the efficiency of LEDs to the strength of metal alloys. Three-dimensional atomic scale imaging like this is bettering our understanding of the structure of materials on this truly fundamental scale.
I have also done a similar work during my PhD and published in 2015. And in this study, what we did was we were trying to image gold nanoparticles, and we were able to get these images on our on TEM. TEM stands for transmission electron microscopy. Okay. But an important thing to note is that this is not the atom itself, but this is actually just the reflection of the atom, because the real atom is very, very small. But using such technique, such as TEM, we can actually see the arrangement of the atoms, for example, like this one. So you can see the dots where we predict the atoms are. So based on the arrangement, you can see whether, for an example, the atoms is arranged smoothly. For example, this one, you can see like it is as if it is a smooth, flat surface. Or, for example, this one, it has the atoms are arranged in such a way that the particles are having some sharp edges, etc. Okay, and to know whether we are looking at the correct atom or what kind of atoms we are looking at, we can also actually measure the distances between each of these atoms. Okay, and this is known as the D spacing. Okay, so this is just some extra information that I would like to share. And as I said before, what we see currently is just the reflection of an atom, because the atom itself is still very, 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 very small. Okay, so I just want to show another video, and this video will give you the idea of the size of an atom, or how small they actually are. Okay, let's watch this video.
In 2013, IBM released the smallest movie ever made. It's a simple stop-motion short film, but what makes it special is that they controlled the placement of individual atoms to tell their story. Everyone knows that atoms are tiny. They're the building blocks of all matter, but I don't think people fully appreciate just how small atoms really are. You see, you can't just use a regular microscope to look at atoms. They're literally too small to interact with light, making them invisible. You have to use a special machine called a scanning tunneling microscope, which basically maps the electrical charges of atoms to create a model representation, like what the researchers at IBM did to make their movie. Even though it seems like we're looking at individual atoms, we're really not. So what does an atom actually look like? I mean, if we were to scale one up to the size of a tennis ball, it would probably look like this. Nothing, and that's because atoms are mostly empty space. Let's take a simple atom like hydrogen, for example. It consists of just an electron and a proton, but the electron doesn't simply just orbit around the proton the same way a planet orbits around a star. Instead, there's a field which shows where an electron might be found, and these fields are what define the size of an atom. The shape of these fields can get kind of weird when you start adding more electrons, but for hydrogen, it's simply a sphere. To really drive home just how empty atoms really are, if we were to instead scale a proton up to this size, the entire atom would be 8 kilometers wide. That means this hydrogen atom is the size of downtown Los Angeles with a tiny electron somewhere within this sphere. It might be 4 kilometers that way, or 4 kilometers this way, up there, down here, or anywhere in between. If you thought finding a needle in a haystack was impossible, try finding an electron in an atom. But let's go back to when our atom was the size of a tennis ball. And atoms come in various sizes, but for this video, I'm making the assumption that an atom is 1 angstrom wide, or 1/10 of a nanometer. Our tennis ball is 67 millimeters wide, making our scale 670 million to 1. A group of atoms like this is called a molecule, and this one in particular's name is adenine. And there's nothing special about these individually, they're fairly simple, but when formed together, they become something very cool. They become the source code of all life, DNA. Now, traditional models of DNA are fairly simple in form, but the problem is that by showing them as a literal twisted ladder, we don't have the context for how small DNA really is, because in reality, it's like 20 atoms wide. It's very, very tiny. And this chain of molecules gets stacked millions of times to form a single strand of DNA stretching thousands of kilometers in length, way out into space at this scale. Molecules get progressively more complex as these groupings become larger, such as with proteins, organelles, and viruses. But at a certain point, they become so complex that they become full-on molecule economies, and we call those cells. Let's take a look at blood. The red blood cell is about 7 microns across, making it one of the smallest cells in the human body. It's important because it acts like a FedEx truck delivering oxygen to the whole body. But even though our scaled DNA would be about 1 meter wide, a red blood cell would be 5 kilometers wide. They'd appear in the sky like alien dropships coming to exterminate humanity. A single drop of blood contains 5 million red blood cells. In fact, your body produces 2 million of these every second. There are trillions of these running through your veins right now! That is such a crazy fact that I wouldn't be surprised if you took that with a grain of salt. I mean, what if you did? Regular table salt is just a compound of sodium and chlorine, and thanks to the way that these atoms are packed together, they form these really cool looking cubic crystals. Because a typical table salt crystal is about 0.5 millimeter wide, that scales up to over 300 kilometers. This is several times larger than the asteroid that killed off all the dinosaurs. An impact of this size would reduce the entire planet to lava, and this guy would be the destroyer of worlds. So it's obvious that with our atomic scale, even tiny things become massive. But when I was crunching the numbers for this video, I discovered something really weird about pennies. I measured this penny at 19.02 millimeters wide. When you multiply that by our scale of 670 million, you end up with a penny 12,743 kilometers wide. Now, why is that special? Well, the Earth's diameter at its equator is 12,742 kilometers wide. Somehow, the penny at this atomic scale is the same size as our planet, with a difference of only a single kilometer. To put that into perspective, the thickness of the penny would appear 950 kilometers wide. And this really helps put into context just how small atoms really are. Just imagine a giant planet-sized disk filled with tennis balls. But now let's have some fun. Remember when we scaled a proton up to a tennis ball and how big the whole atom got? How big would a penny be at that scale? It would be 1.5 billion kilometers wide. That is the size of Jupiter's orbit around the sun. That is incredibly huge, but can we go even further? Just like an atom, a proton is also mostly empty space. It's actually composed of a bunch of subatomic particles that we call quarks. According to the standard model, quarks are actual literal points with no physical size at all, because size is kind of irrelevant at the quantum level. However, there is some evidence that perhaps a quark is about 2,000 times smaller than a proton. So if we were to scale a quark up to the size of a tennis ball, how big would our penny be then? It would become hundreds of times bigger than our entire solar system, coming in at just under 1/3 of a light year in length. But now we're on the cosmic scale, and suddenly this massive penny becomes tiny again. I mean, our closest neighboring star, Alpha Centauri, is about 4 light years away, and it would take 14 of these pennies just to reach it. In comparison, our Milky Way galaxy is 100,000 light years across. What do we have to do to put a dent into that scale? There is a unit of distance that is considered to be the smallest length mathematically possible before the laws of physics fall apart, and it is called the Planck length.
Now, this is a length of a Planck, but this is not what a Planck length is.
It measures out to 1.6 times 10 to the negative 35 meters. And I realize that number might not mean much to you, but this is a number so unimaginably tiny that if we were to apply our tennis ball scale, our penny would be bigger than our entire galaxy. Except to say that is an understatement would be an understatement. The entire observable universe is 93 billion light years wide, and our Planck penny would be 90,000 times bigger than that. Let me show you exactly how big that is. If we were to confine the entire observable universe into just a single pixel on a 4K TV, you would need over 800 TVs just to see our entire penny. That is how small the Planck length is. Infinity goes both ways. Our universe is inconceivably large, and yet it is also inconceivably small. It really feels like a fractal with no end in how big or small it can possibly be. Our only limit is how far we can see. Thanks for watching.
Look, why are you acting like this?
Why? That's why.
Okay, coming back, now you know that everything or every matter in this world is made up of atom. So the question is, Why are the matters not the same if they are being made up of the same atom? So we're going to discuss that in the next video.